traditionally what traditionally what we used to do is we used to have a big warehouse servers. Maybe it could be in Oracle and maybe in Netezza or Teradata, right? And we used to build a warehouse on it. So problem with like before problem, like what it used to give us is you used to dump a lot of data into it, into that net, that business specific or that technology specific format. And that used to handle all your ACID compliance, processing of your data, and then also tuning of your data, tuning of your queries, and lying down your data files in that specific format. Maybe it's a nature that has its own format, or Oracle its own format, right? So now the problem with that was like you were not able to scale up, right? If you were talking about the big data, you were not able to scale up. It was costing a lot of money because you have to make sure it runs 24 hours. And also it brings up challenges because now you are tied to a vendor, right? You are stick with a specific vendor, and you can't move ahead into a like open way or using open source or using other vendors. And another main use case, it only used to have a structured data set, not the format like unstructured format like images, audio, which new data platform has to support it to give a better, to support ML use cases. So now if we go into Data Lake has promised like it will support all the structured, unstructured data source, which it has supported. And we a lot of data gets ingested in data lake from various sources, and also it provides is various analytical tool we're able to consume from data from this data lake. So that kind of democratized the use cases of data. That democratizes, people started building a lot of use cases out of it, but it gave us some challenges, right? Challenges uh, basically in terms of getting the ACID compliance like traditional warehouses, how to maintain your query performance better, how to manage the isolation level like traditional warehouses used to give, like those kind of things, right? So now now we come into the data lakehouse. Data lakehouse basically is a combination of your warehouse features, best feature of your warehouses, and features that data lake provided. Data lake provided is scalable storage, is because of the object store. Maybe it's Amazon S3 or GCP storage. And data lakehouse started giving you the benefit of warehouses because of the ACID compliance, uh, isolation, atomicity, and consistency. So how that data lakehouse, that feature is through the invention of table format. So even before going to table format, right, we traditionally used to have a file format called Hive format. Basically, it got developed when we started using a data lake. So what it gave, feature it gave is basically all the data in your on your data lake can be now accessed through a table format. So you can access your data underneath certain object store like you are accessing your database and tables. So to give you that feature, right? And with that feature, we solve a lot of problem, right? We a lot of query engine used to support it, and it did a good job on what it was promised to do. But the few challenges it brought, right? Let's see what features it gave us to it, and then we'll move to challenges. First thing, now you are getting a file format, right? So you are accessing your data like a table in your traditional warehouses. So basically, table tracks your location, and that abstracts it as a table in your Hive catalog, and which you can query. And secondly, efficient queries. What do you mean by efficient query? Here is the Hive started when we started using Hive, it allows you to partition your data, right? So basically, you can now send a query filtering into certain based on certain key fields, and then just read only that specific data from that specific partition, and that basically solved also help us to run your query faster. And second thing is it help us to manage store your data in a directory structure, which basically help us to read the data from various formats and in from various engines. So that is the best part, right? It gives us partition in some way. It helps us to solve to run our query faster. It helps us to run your structured data into a structured data in a table format. So now you can do select asterisk on that table and then run a query. And a lot of tool, right? A lot of engines supported it, which means like you don't need to stick with specific vendor SQL engine. If you can use open source, many SQL open source tools like Hive or MapReduce or Spark, you name it. So many supported it. So that kind of advantage it gives, but it also gave us some challenges. What challenges it gives is first is no support of transaction guarantee, right? So it didn't support the uh, SE transaction, the atomicity, consistency, and isolation and durability, right? So that's a challenge, and which is required to run your large data processing pipeline, right? That makes your data consistent and that makes the reliable data for your upstream consumption or upstream reporting. Second thing is lack of metadata, right? So why lack of metadata is now, if you see, right, in Hive, you have a file format like Parquet, which is having statics and statics about the data, right? And the data itself. But we were not properly utilizing it to prune the data, right? To filter out unnecessary data. So that was lacking because that metadata was lacking. We were not efficiently pruning the data before so that before which impacted like reading your whole data again and again from your file store. And third thing is schema evolution. So when you were using data lake in a Hive, like schema evolution was getting a challenge. Adding a simple column, right, was very cumbersome and also a troublesome, right? So so it what it impacted is you need to like whenever you add a column or rename, it has a heavy like scroll on your platform, right? It used to take a lot of time for the development to come with new detail and update your data to streamline your new maybe building ETL pipeline or building reporting. So fourth thing is about partitioning, right? The partitioning was a big solution, but also a problem because underneath the file system, we have to lay out the partition structure in S3 object or SDFS. Because of that, now what you need to do have to do is every time you change your query or there is a requirement of change, you are going to filter by a different key, then those partition layout under the S3 object or SDFS should be recalculated, right? Reapplied, and uh, that things needs to folder structure needs to be created in your store, data store. But for small table, it might be fine. But for the big table, yeah, it's a challenge. It's a time consuming and you can say error prone as well. So these are the challenges that I give us, and which kind of solves by table format. So in a market, you can see a lot of table formats that are coming up. There is Delta Lake from Databricks or Hoodie, and this Iceberg. Here we are going to talk about Iceberg, but all this table format is the same in some way, but uh, there are some differences. Again, needs to be chosen based on the use cases and things you want to do in your data platform. So basically, between three, always based on use case, we can choose the which table format to choose. As we are going to Iceberg this time, reading about Iceberg, so I'll focus on Iceberg. So first thing is we need to make sure is file format like Parquet and table format are two different things. Even though the table format uses a Parquet to keep some metadata information in some cases, but they are different. Here in table format, in table format, in table, sorry, in file format, like Parquet, which is where your data actually resides, where the files are kept with based some statistics like grouping your rows, columns together, and with basic statistics about mean max, null counts, all those statistics about your table into Parquet format. So, but table format is on top of your file format. So your Parquet file is a file format which is keeping your data, but table format, it provides a management layer on top of your file format. So what management layer what kind of layer it provides is it helps you to track schema. So it now helps you to know what is the schema of your table. It can help you to partitioning your data. It has that information about partitioning, file level metadata. So, and also different metadata that helps you to process your data efficiently, and pruning of your data happens smoothly when you are reading or writing data from in your data lake or in your lake house. A table format also is, like gives you the flexibility of your running query, and because it has many features are inbuilt to help you to do day-to-day jobs. What I mean by that is with table format like Iceberg, they have a lot of automation done. For example, is like optimizing your table, right? Deleting your old data. All those things can be done easily in the format like Iceberg, which takes a lot of burden from you when you are administrating your data lake house. So these are the benefit, right? It provides a layer on top of your file format so that you can query it like a normal table database. And additional to that, it keeps the track of schema, partitioning, and different statistics about your data so that it can help you to maximize the performance and also provide the flexible way to do schema evolution, schema partition evolution without changing underlying data. So yeah, so as we were talking, right, this gives ACID compliance. That is one of the feature of table format like Iceberg. And with the ACID compliance, basically that is giving you a data integrity and data consistency. So atomicity, as we know, either everything goes successful or nothing, right? So that is the atomicity. Consistency here is when we are having a concurrent write, right? Iceberg provides a snapshot so that you are not two writers are not conflicting with each other, right? So that your writing goes through smoothly, and the reader gets a consistent view of your data when they are reading it. Third is isolation. So as in the databases, like there are various level of isolation. Here in Iceberg, it provides snapshot level isolation and serialization isolation. Because of both together, we are achieving the separation in your concurrent reads, concurrent writes into the Iceberg tables. And durability, of course, it's going to use the S3 object store or any object stores or SDFS in that case, and that are durably written into that system, that into that store for the durability of your data. Another Iceberg feature is time travel and rollback. And this is the most important feature. This is the most important and most needed feature as well when we are building a data lakehouse platform, right? So when we are building a data frame, sometimes you may write a wrong data into your table, right? Sometimes your merge statement might be logically wrong, but you execute successfully and you have written that data into your system, into your table. In those cases, time travel and rollback comes handy. In Iceberg, this feature is there, so it helps you to recover faster. So if something has gone wrong, you can just point from one snapshot or one point to previous where it was everything correct, so you can revert back. That helps you to recovery. And also, if you want to see how the data has transformed or data has changed in your that specific table, you can have a look with this time travel and rollback feature that Iceberg provides. We will talk about how these are achieved in Iceberg. We'll talk about that later. But this feature, basically, time and rollback helps you to recovery, and you can see the historical access or how your data has transformed. You can see that with this. Another two important things is schema evolution and partition evolution, right? So partition evolution is basically when we were using Hive, we used to partition based on key value and have that layout in your object store or SDFS. But with the partition evolution is you will change your partition based on your requirement, but that does not require you to change your underneath data, or you don't need to rewrite your data. What it basically is, it will be just a file level or metadata level operation. You are kind of just a switching in a updating a file which keeps the track of the partition, but not changing the underlying data layout. So that helps you to evolve your partition based on your requirement. So schema evolution is like you can add column, remove column, and that is guaranteed. It will not impact, and it will not impact anything, and it is a constant change. So which both are the most important features for the data lakehouse. We'll see this how this happens in the coming up coming up part. So all the features we talk about, rollback, right, schema evolution and partition, all those things happens because how Iceberg has maintained or created its architecture. So going from left to right, first there is a catalog layer, right? So catalog traditionally can be a Hive catalog or Spark catalog or Glue catalog or Apache Iceberg catalog, right? They can be anything. Based on the catalog, it depends what kind of feature it gives. But the purpose when we are writing or reading, it just contacts the catalog and does the operation of read and write. But there are few features that are catalog dependent as well, like NIS. Like for example, Apache NIS catalog can give you more features than traditional Hive or Glue feature. One example of that would be a multi-table write, right? Like if you are trying to write a multi-table, then those are not supported by other only few Apache NSC and others supports it. So catalog where your table information are written, where the table information is written into that specific catalog, which can be your any catalog. In this case, let's think it's a Hive catalog, right? Now that's a catalog layer, right? Keeping the maintaining your information about the table, right? Then we have a metadata layer, right? Which is the most important part of this Iceberg architecture. The schema evolution, partition evolution that you are getting is through this mechanism. And the performance that you will get for your query execution is because of this metadata layer. So in metadata layer, you will see metadata file, manifest file list, and metadata file, manifest list, and manifest file. These three, a layer helps you to achieve what we just talked about. So let's see what are those, right? Metadata file. So metadata file is basically a JSON file that points you to specific that maintains and keeps information about a snapshot. So what is snapshot? Snapshot is your point in time position of your data, right? What was the data point at that specific location? So currently you can say it's at snapshot 0, but as your time grows, as you made changes into your table, the snapshot will continually increasing. And because every changes creates a new snapshot, that information is maintained in metadata file, because of which you are getting the feature like rollback or time travel back, or also how you are getting concurrent write into your table. So metadata file keeps the information about your snapshot. It also keeps information about your schema. So whenever you are reading or writing on this table, your engine, whatever engine you are using, it gets information from here and then does necessary operation. So let's say in this case, we are using snapshot 0. Let's say this is the first operation. Then that snapshot 0 will have a manifest list file that basically has, again, the statistics about your data, like upper bound and lower bound of your partition key, what is your partition spec ID, those kind of information which are required when you are reading and when you need to prune your data when you are running any SQL queries, or when you are doing any operation in this Iceberg table. So you have the manifest file, and that manifest file again keeps the track of manifest file. So manifest list keeps the track of manifest file. That manifest file is again keeping the track of your actual data files, which is in your 3 data layer. So if you see, metadata file is keeping the track of what are the snapshot, what are the latest, and what are the old version of snapshot. And also it is pointing out what is the manifest list, and that manifest list will point out to the manifest file that keeps the track of your data files, which is written in Parquet. And additionally, that manifest will keep track of your max minimum value of your column, how many nulls are there, like various statistics, again, to help your to boost the query performance and to do the pruning in your read operation. So one thing data layer also has is a delete files, which is not here, but that will be skipped when reading. But whenever there is a delete operation happening, then the delete file will be created, but that is skipped when reading. And that is also a file that you might be seeing when you are doing any delete operation in that data layer. So whatever I have explained earlier, right, it's a graphical view of it. So The catalog will be there, keeping a pointer of your current metadata for that layer. Let's say in this case, we start with, you created a DDL, which it starts with snapshot 0, and then it keeps the track of manifest list, and it keeps the track of what are the manifest file for that specific snapshot 0, and that is manifest file will keep the track of data files, which is your actual Parquet data file. So let's say again, now you made some changes, added files, some, or deleted some files from your data files. In that case, it's going to create a new snapshot, right? If you see in that metadata file, you are seeing S0, S1, which means there are 2 point-in-time versions. So S1 is a manifest list that keeps the track of manifest file. Again, that this file will keep the information about the what are the partition used, what are the statistics, what are the operation that created this file, right? Those kind of metadata will be there that helps again in your query execution time. So this is the summary, right? So everything is tagged, everything is indexed in this metadata layer, because of which you are getting ACID compliance, snapshot isolation, right? And also getting the schema evolution and partition evolution because of this meta layer, because it keeps a track and everything is a metadata operation, not the file level operation. So we talk about how the metadata layer works, right? Let's see now how it actually works when you are doing a write operation. So when you are doing the write operation, right? Write operation here, I mean, maybe you are doing an insert or you are doing a merge statement, right? Anything that is a write operation, merge, update, like that. First, you will send that into your engine, right? Maybe this time it's a Spark engine. When it gets, Spark engine gets it, it will do the query planning, it will do the parsing, it will do the build up the execution plan. But for the execution plan, it needs certain information, right, regarding the table. So information like what is the schema of this table, right? And before that, what is the latest uh, snapshot, what is the current snapshot metadata file for that table, right? So now it will go into that catalog, whatever is your catalog you have used for this case, it will go into that catalog, get the latest manifest metadata file, look a name, and then get into the engine, right? So when you are getting that information, what it does is it will give you the hex ID or new file name, depending upon the catalog, it will give you that information. So that information is required when you are writing back into when you are swapping your metadata file. I'll talk about that again, but that is the hex ID for the new metadata file will be created, and that is passed into engine and with the schema and partition information. So now what firstly happens in step number 3 is, now based on your query plan and all the schema partition information, now whatever the transformation you have defined, based on that logic, the data files will be created, right? The Parquet file will be created in your S3 object or in your SDFS. So once that data file has been created, what happens now is the manifest file will be created. The manifest file here will track the data files. Basically, what it keeps the track is, okay, this file, it has the data from maybe from this to this date, or what is the null column, null count in that table, right? Various statics of data, and keeps the track in the manifest file. And it writes the manifest file, And then it also creates the manifest list saying, okay, I'm the manifest file for this snapshot, and these are my manifest file. And these are the statics that I have received, gathered while I was writing the data file. So that all thing information will become down to a manifest list. And once the manifest file has been created, then what will happen is it will now go talk with the catalog and try to update the or swap the metadata pointer from the old one to the new one, which got recreated in this operation, right? So it will try to swap. Now, if the swap, if there is already some other job has already swapped it with another swap with other by another process, then what will happen is your current, even though it has got that hex ID, it will fail because another has successfully written and swapped the metadata pointer. Now this failed one will do the retry, and in like subsequent, maybe in first try or second try, it will succeed and swap the metadata pointer. With this, what does it means? This is how it is allowing you the concurrent write into the iceberg table. And that's how you are saying, like, if the process, if your job that is writing a table is dead, is failed in some state, and it failed to update that pointer, you are basically safe, right? Your data files may be orphaned in the system in that table, but you are not changing a metadata pointer. So this is how you are getting that optimistic concurrency, right? And then you are getting the isolation, and also you are getting concurrent write feature with because of this step, how it does the swapping of metadata pointer. So yeah, that is the whole overall step how it writes it. And one thing we need to be aware of here is there is a concept called copy on write. So basically, whenever you are doing update or inserting into this specific table, right, you can have, or by default, the table will be on copy on write. What does that mean is if you are doing any, for example, if you are doing any delete operation on that specific table, it is going to copy the impacted data file and then do that operation, right? Uh, and then copy that operation and then leave it there. So what will happen is, so it will just copy that file and do the update of that impacted row in that space file, and your job will be metadata pointer will be updated. So basically you are creating a new data file in every write operation that is happening. So that is a problem, right? If you are doing some write heavy operation and you are doing, or you by default it is doing copy on write, meaning every time you are getting some latency because of that operation. So you need to choose, you need to turn it off based on the use cases and choose other option so that you get the benefit, your use case suits the need, and that suits, you choose the specific methodology based on your use cases, either copy on write for your table or merge on read for your table based on use case. So read operation in Iceberg. So now the pattern it follows is similar to the how write operation happening, right? Basically, first your query is sent to the Spark, whatever engine you are reading to read the table. It will send to it, it will parse, it will talk with catalog, it will get the pointer to the latest metadata, it will get that, it will get the latest snapshot that it has to read, and it will get the um, snapshot it has to read, it has goes to a manifest list, it knows what kind of what manifest file it has to use for that specific query. And with the manifest, when it goes to manifest file, now it knows the min and max, all those statics about the data file. right? It will select that specific data files that are related, that are needed for to satisfy that specific query, and then returns the result to the engine, right? Whoever is reading it. So throughout this process, right, the metadata file, manifest list, and manifest file is helping you to prune your data and helping you make your own query faster. So whatever engine you are using to read it, it will use the indexing that metadata is providing to run your query efficiently and to prune your data, um, and prunes your data so that you are not reading extra unwanted data from your S3 object or SDFS. So here the one concept is that when you are reading, there is a one called merge on read. So whenever you are reading, you can set the table in operation mode in merge on read. Basically, what that will do is whenever you are reading the data, the delete files that are created by the write operation or update that happened, it will try to and give you merge that and then only give you the result back to your engine. So merge and read is a one strategy that we can choose when reading it, but again, that has advantage or disadvantage based on the use case. So we need to select what mode to use in your read operation. We have to basically carefully select what we need to use for your specific use case. So summary is like the metadata layer. Whenever you are passing read query, each layer utilizes the statistics and utilizes the mixman, mixmax, uh, statistics, upper bound, those kind of information to prune and to run your query faster. So that's a pretty much on the read operation in the Iceberg, right? So now I'll walk you through the metadata creation, how the metadata looks like in our demo, and I'll give one of the quickly walk you through the write audit publish feature that Iceberg provides, and we'll just walk you through that as well. So now let me share my VS Code screen. Give me a second. Are you able to see the screen?
Yes.
Yeah. So yeah. So I'll quickly walk you through this demo sample that we have created for this demo, is for this session. So dataset wise, I have used a taxi NYC dataset. It's a very small, a few GB, but I think, brought it to some MB and then use it. So that's a dataset. And what I have done is here is I have created few helper scripts, right? One class that has a few methods on it that does certain operation. For example, one is run DDL, one is insert, one is delete and merge, and some other like building bronze layer, silver layer, gold layer. And to run those above execution script, right? I have used a concept like here is like I'll use the first use case that only executes the DDL. DDL just runs a table definition, so just creates a table. Second is it will write some data to it. And third is basically it creates a brown, silver, and gold layer. In the script, it will basically does the series of transformation, it reads the data from browns, creates the silver, reads the silver, then creates a gold layer. And fourth one is a run WAP use case. Basically, that is I wanted to show one of the beautiful feature of Iceberg, how you can do data testing, data quality testing using a web feature that Iceberg provides. With said that, if you come down here, we, as usual, when you are creating Spark, we need to create a session. But in that session right here, there are a few things are different. One thing is this you might have regularly seen it, but one thing different is this one. So basically, we need to provide Iceberg as a Spark runtime, and we have to specify version of it. So that's one part. Second part is Spark SQL extension. This is the important feature. The main feature is the important part. Important thing that it does is you can run various details or store procedure that Iceberg provides. Like for example, Iceberg provides store procedure to clean up your storage, to optimize your file storage, right? All those store procedures can only be executed once you have this SQL extension. Coming up here is your catalog. Right now, I'm setting up this Spark catalog, and the local, because I'm doing a local, it creates a catalog name called local into the local system, and which I'm using right now. And I'm using this location as a warehouse storage location, which we'll see how it in our this VS Code as well. And this is the format that, because of the local testing, I have to specify all those things, and just invoking the class, data class processing pipeline, passing up the Spark context, and that will help us to execute all these use cases one by one, which I will be showcasing after this. So yeah, so that is the script. And now I just need to run that. So first I will run the first use case that will, on the back end, what it does is just executes the execute DDL that is going to create a table called Browns, NYC Browns table using Iceberg format, and it's going to create silver table, and with a partitioned by day, this thing, right? The one thing, if you notice here, right, in traditional Hive, we used to just do a partition by and then provide a column name, but that column name should exist in your schema, right? So if you say, let's say you are doing a month, that month should be here in your schema, right? But Hive has abstracted that away, right? So what you need to do is that column, whatever column you want to do partition on, no need to be here in your schema. Simply, you can provide on what column you want to partition by. Let's say you want to partition by on this column, but you want to do a filter on a day, let's say, you can simply provide this transformation, and the column underneath it, it will create that column, it will create that partition logic. And whenever you are reading or writing, it will use that logic to do your partition pruning, right? To prune your data files, what data files you read or not, that information will be done because of this information. So partition by, and this is called hidden partitioning in Iceberg. So this is the transformation, this is a column you are going to do partition on. So that's the thing. So, and similar, it will create a gold, create a gold table. So let's execute this first script. So right now it has completed quickly because we are just doing a DDL table creation. So as showed earlier, we have now the warehouse location. It has created the three tables underneath this folder structure. Uh, Bronze is a one table that currently we are looking into. So if you see here, right, you have underneath your table name, there is a metadata folder. In the metadata table, you can see a file called v1.metadata.json. This is the metadata file which we were talking earlier that catalog points to, right? So this is that file. So here, if you see, right, it has a lot of information, but let's see what are the things we discussed earlier are here or not. So first thing we talked about, it keeps the partition information, right? So all the partition specs will be filled here because the Browns doesn't have a partition thing. It doesn't have that information here. So partition information is indexed or tracked in your metadata file. Secondly, we talked about snapshots, right? Metadata file, a metadata file will keep the track of snapshot. Currently, because we just created a table, it doesn't really have a snapshot, right? If you see here, there is no snapshot ID. Currently, it's a kind of zero situation. There is nothing, just a metadata, just a DDL file, but nothing is there. So snapshot, we'll see in next use case execution, we'll see some information populated here, right? Some information populated in other case, how that information, like how the table got created, how that table on that table, how the information on that table got created, right? So additional thing we talked, it will create a schema track, right? So here is the schema information for that specific table. So this kind of information about the table are tracked and populated in every metadata layer that we discussed earlier. So now you have seen the metadata, the JSON. Now let's re-execute our second use case and then I will walk you through again. So I have re-executed second use case. So basically what this does is it's going to write into the Browns table. Okay, I'll show you that script as well. So what it does an insert. Okay, so I'm statically putting some data, and that writes into the Browns table, right? Let's see now what difference it does, right? I'm just inserting few records into the Browns table, and let's see what difference it does. So if you see right now, previously we only had the metadata layer, right? And now we have a data folder. So so now what it's doing is, based on the folder, it is separating all the data for you. That specific table will go into a data folder, but the metadata for that table will go into under the metadata. Now you also see here that there are two metadata versions. First, V1 was from our first operation and V2 from the second operation, right? Now, if we see, this is our latest metadata file. And now if we see here, we'll see all the schema information like before, right? Now, because we don't have any partitions done, there is no that information. But one thing you will see is what operation created that table, right? Information, what operation wrote the table in that specific file, right? In that specific snapshot. So those kind of information you are seeing here, how many records got added, right? All those statics are here. And this is our snapshot sequence ID is 1, and sequence ID is here, and the number is 1. And also it points out to the location where is your manifest list, right? This is the list, manifest list, which will be in Avro format. So there are two format, right? One is JSON, that is pointing, giving us some information about the where is the metadata list file. So here it is points out to that. Now metadata manifest list file will be in Avro format. So which will be, if you compare, if you see the number 1153, that should be the same number here for the snapshot ID, and which is manifest file, right? So this manifest file is an Avro. We can't really see it because it's Avro format. If we had used any tool, we could have inspected it. But what information it contains is, again, the statics about your table, right? Like min, max, upper bound and lower bound for your partition key, some statistics, how to tune your manifest file, right? Those kind of information, again, will be here, populated here. And other thing that it has is what are the manifest files for that specific snapshot. So snapshot one, manifest file is this one, 49 at the end is the manifest list, and that it points to manifest files. Again, manifest file will be in Avro format, right? And which we can't see right now, but that manifest file will be in Avro format, that will be pointing into different data files based on the different statistics and different based on different thing. It will have a different manifest files, and that will keeping track of different data files, again, to help your query processing. So this is the Avro manifest list file. And that again said it's Avro, so we can't see, but again, it keeps a track of your data, different statistics of your data. So third thing, we can just run. So we have run this executed, right? This third use case, which basically populates. Oh, I think I did something. Okay, basically that needs to populate the data onto specific location and few things we can see here is the version one. So as said, we have done a partition on this table. You will see a column and what transformation on that J for the partition. So those all information are tracked. And because of this, you can do a partition evolution, because it's not a file level, like file level operation. It's a metadata layer operation. You can easily evolve your partition as your query evolves. Now going to last use case that I just want to go through is write audit publish use case. Basically, if you have played with Git, how we used to do feature development is you will do a checkout from your main branch, and you keep updating your feature branch. And then once you are okay, you tested your feature branch, then you will create a pull request and merge into the main, right? So into main. That is typically how we commit our codes and push our codes to production. So in the same way, in the same concept, Iceberg provides a feature where you can create a branch out of your data, right? Out of your table. And then you write into your feature branch, right? And paste the data in that specific feature branch. once you're happy, then you can do kind of merge into your main table branch. So how that is done, I'll show you. And that is which is a distinguished feature from rest of the table format. So I'll show you that. So basically, if you want to enable that WAP, write audit publish feature, you need to enable that feature, right, on that specific table. Then you need to create a branch out of that table. Right now, I'm creating a static branch name, but whenever you are doing testing, maybe you need to use some other prefixes to create that branch out of your main. The main will be your table, always will be main, right? Your main table will be always a main branch. So we'll check out a new branch out of it, right? We write some test data again into it, right? And we do some counting. This is not actual data testing, but I'm just showcasing what things you can do now. Because you are writing into this branch, now you can do your, whatever data quality checks you want to do, you can do on this version too, like this kind of using that, like this kind of statement. Maybe this time I'm checking a count. And then what you can do is in line number 194, you can do is, let's say, everything you did test on your feature branch in that specific v2 development branch is okay, and you want to push it into main, merge into main. You can call the store procedure. This is where that SQL extension that I talked earlier comes to play. So this is provided by that SQL extension. You can call fast forward, which is basically tells, okay, bring the changes from v2 to main, and that will bring it to the main. And then you can have, again, you can do the checks. And yeah, basically that way with the WAP feature, you can test your data, and then once satisfied, you can merge back into your main table branch, and you can do a data quality test in your pipeline without much hassle using Iceberg. And which is, this feature is a very, I think Iceberg only has this feature so far. So yeah, that's all. Now I think we can open up for question and go from there. Gurmukh, yeah. Hello.
Yeah, thanks.
Yeah.
Thanks, Raj. So let me see.